Want to find electric potential due to a dipole at some point P. So the end points of the dipole are A and B. So there is a positive charge at A, which you call as Q, and there is a negative charge at B, which you call as minus Q. So the length of this dipole is 2A. So from the center, the charge Q is at a distance A, and from the center the charge at B is also at a distance A. So say you have the origin at the center. We want to find the dipole at a point P, and this point P is at a distance r from the origin and makes an angle theta with the horizontal axis. So the coordinates would be r cos theta and r sin theta. So let us draw this. So distance is r from the origin and it makes an angle theta with the dipole. So distance from A to P is say RA, and distance from P to B is RB. Now let us assume that the charge at A is QA and charge at B is QB. So you write charge at A as QA and charge at B as QB. We will later on write QA as Q and QB as minus Q. So the potential at P is now sum of potentials because of charge at A and at charge at B. So total potential at P would be K times QA over RA plus QB over RB. So RA is distance from A and RB is distance from B. Now we want to talk about RA vector. So earlier we were talking about RA as distance. Now we want to talk about RA as vector. So RA vector would be this angular bracket r cos theta comma r sin theta minus coordinates of point A. Now origin we put at the center, and therefore coordinates of A are minus A0, coordinates of B are A comma 0. So RA vector becomes r cos theta plus A comma r sin theta. So this is the RA vector. So length of RA vector is square root of r cos theta plus A square plus r sin theta square. Now similarly we compute RB vector. Now RB vector would be coordinates of point P, or you can see P is nothing but OP vector, which is r cos theta comma r sin theta minus A comma 0. So the vector you get RB vector is r cos theta minus A comma r sin theta in the angular brackets. So this is basically nothing but r cos theta minus A I vector plus r sin theta j vector. So we have RB vector from pointing from B to P, that is PP vector. So the length of RB vector would be r cos theta minus A square plus r sin theta square. Now the potential we computed before we wrote as V is equal to K times QA by RA, and QA is Q, plus QB by RB. Now QB is minus Q. So you take Q out, you get potential as, so QA is Q, QB is minus Q. So you get potential as KQ times 1 by RA minus 1 by RB. And this RA and RB are nothing but length of the vectors which we have just computed. So RA is length of RA vector and RB is length of RB vector. So case 1 say theta is pi by 2. So in that case RA vector length is equal to, notice that now cos theta would be 0. So I'm just copying what we had derived before for length of RA vector, and now you put cos theta as 0 and sine theta is 1. So you get length of RA vector as A square plus R square. So cos theta is 0 and sine theta is 1. And length of RB vector, again copy down the formula, R cos theta minus A square plus R sine theta square. Again cos theta would be 0 and sine theta is 1. This will again give you minus A square plus R square. So this is square root of A square plus R square. So notice that theta is pi by 2 means P lies somewhere with the red dot I have made. So at that place the angle theta would be pi by 2. So we can plug this length RA in 1 and you can see that RA is equal to RB. So V would be 0. So the potential at theta equals to pi by 2 is 0. Case 2, theta is 0. So that is theta is 0 means that point P lies on the same axis or the same side as dipole. Now if theta is 0, sine theta would be 0 and cos theta would be 1. So RA would be square root of R plus A square, which is just R plus A, and RB would be R minus A square, which would be R minus A. Now you plug this in the potential and you get KQ times 1 over R plus A minus 1 over R minus A, and this gives you KQ over R square minus A square times minus 2A.